just possible. But thank you for coming. I think you'll see that our students have learned a lot during their time here, and that they're able to accomplish a lot. They're ready to go out into the workplace and tear things up. Not literally. All right, Dr. Carrie Hall has the first theme, and Carrie, I'll let you introduce your students.
Good morning, everyone. I would like to introduce Daniel Griffith and Casey VanWinkle this morning. They've been working very hard all semester on a structural engineering project that I'll let them introduce right now.
Good morning, everyone. Like Dr. Hall said, this is Daniel Griffith. I'm Casey VanWinkle, and this is our senior design project. Basically what we had is a steel structure in Fort Hood, Texas, and we got the project from Hodge Design Associates here in Evansville. And basically what we had to do was design the thing from top to bottom. We start all the way at the top at the roof decking and find the loads applied on there, and then move to the roof joists, and then those loads apply to the steel beams and then to the columns and so on, all the way down to the footings. This is just to give you a better representative idea of what we're working with here. This is the front view of the structure. And as you can see, it's a dual food complex, which is a Burger King complex. And this is just north-south elevation, just to give you more idea. Here what we have is a plan view. It's showing you where the beams and the columns are located. And the red dots are all the columns, and those columns go all the way down into the footing. And the beams span from between every one of the red dots. And as you can see right here, here's our maximum loading area. This is the maximum span here, which is 29 feet. So in this area is where we had to do our structural analysis and find the maximum columns and beams. And we started off by finding dead loads. The dead loads are basically everything in the structure. It's everything that's not moving and that's going to always be there. And we found most of the values from ASCE 705, which is an engineering handbook. And we basically went through there and we picked all of the design criteria that applied to our structure. And after we found these, we then started designing, and we found all of the weight of all of the designing weights and applied those to all the way down.
So once we did the dead loads for the structure, we moved into some of the environmental load calculations on the outside. And this design process actually happens simultaneously when we're picking numbers in order to get the best loads for the geometry coming out. Like we said before, you design top down so you get the loads on the top, so you can design the steel decking and so forth. We'll cover that later. Moving into some of the more robust calculations for the environmental loads, we have wind calculations. In order to calculate the wind forces on a given structure, you first have to go into ASCE 705 and classify what region your structure is going to be constructed in. Based on the 100-year maximum wind expected in a given area, you get a base wind load that goes on the structure, which changes in elevation. The further away from you get, the larger wind forces you get. So for a single-story structure like ours, you don't get that large of a wind force on the side. But as you can imagine, for the taller structures, it becomes an issue increasingly fast. Four main wind forces you get are the windward, leeward, sidewalls, and roof forces. These are all calculated at each direction the wind hit the building from. Then you get what's called a structural envelope of forces. So you take the maximum value for each one of those directions and apply that as the worst load case for the entire structure. Diagram here shows how from the windward side you get an opposite force of leeward wall, and the roof coming down ends up with an upward force on the outward side. So you design out the pieces of the structure to make sure that you both design to sustain gravity loads and uplift forces. Moving into the seismic loads, it's important to note that when you're doing seismic calculations, you actually have to do a preliminary member design for your structure, because the amount of seismic force a structure feels is actually based on its proportion to its own weight. So you have to have a general understanding about how big your numbers are before you can calculate exactly what forces are going to experience in a seismic loading event. But after we went run through the calculations, and we'll cover that again in more detail on the next slide. We know maximum values of shear, 34 PSF for the walls, and 4.42 PSF for the roof diagram. You calculate the snow loads similar to the seismic loads. You have to again go to ASC 705 and figure out what category of the structure should be built in and what the ground snow load in that area is expected to be in a given weather year. The rest of the loads have been proportional in the equations to 705 for how deep the snow is expected to be on the ground and how long it is before that snow melts. You then calculate what your snow drift is going to be on the top of your structure based on, again, that ground snow load and how tall your parapets are, so the maximum height of snow can achieve in a drift based on the distance between the exterior of your roof walls and the exterior roof diagram. You then have a couple other surcharges. For instance, if it rains on top of snow, you get additional loading, which transitions me into my final loading phase here, the ponding. All your structures you see around actually have built-in roof drains of one type or another, whether it just be your standard roof structure for your buildings, your homes that have gutters on the outside, while industrial buildings and small steel frame buildings have internal roof drains where everything drains in and then is pushed out. Which you can imagine sometimes those drains clog. Then you get some pretty bad loading scenarios where you get roof ponding. And that's what our worst case here was. If you have roof drains clogged, what the maximum weight of the rain on top of the structure would be, it actually didn't turn out being worse than the snow, so it wasn't a controlling scenario. Moving into the roof decking design for our structural members, these were actually picked from using the Volcraft design guides. And that's just it's a global company that have local facilities here in Indiana, and they're actually focused on using recycled materials to reduce the environmental impact of structures. So it's a good company to be working with. They have comprehensive design guides for both their steel decking and joists that we'll see today. So moving through, we actually chose the 1.5B22 deck type. As you can see down here in the diagram, the 1.5 refers to the depth corrugation on your sheets. The B is the standard nomenclature for their wide decking, so that means they have a wide distance between their corrugations, 6 inches here in our case. And the 22 refers to the gauge of steel you see. That's the lightest gauge of steel you can buy for roof decking, and that's all that our loads required for our structure. We simplified the design and we have one span between joists, so that we have a constant force in all the roof decking, so there's only one type required. The number of support fasteners and the type, we used screw fasteners. It's just easier to get up there and screw the things down than just to go through and have skilled welders come in and weld all the sheets down. Also, in case you have some sort of construction issues, it's easier to unscrew the piece and move it to a different location, something like that. Side lap fasteners are actually where your sheets overlap here. This is not always going to happen on the joist, so you actually have to make sure the sheets are adhered to each other with side lap fasteners, which is a different type of screw. The deck fastening pattern, is 36 and 7. That's 7 of the number 12 key K screws for every 36 inches of steel sheeting you have. And that just ensures that, again, with the upload forces that we talked about with wind, you're not going to have some sort of event where you're pulling off roof sheetings like tornadoes, for example. And the number of side lap fasteners is 4. So for every 36-inch section of this, you'll have 4 screws on the side, making sure they're held together securely. Moving into roof joists, again, we use the Volcraft design guides to design the roof joists. And these are actually bar joists, which is a different distinction from some of the similar trusses you might see in structures of this size. It's a much lighter building material, much more efficient for spanning open spaces of smaller structures. We had 3 distinct spans given to us basically on the architectural drawings. You saw that we had different spaces between each of your interior lines of support and columns. So we had 3 spans for the joist to cover. Spans of 25 feet, 4 inches, 21 feet, 11 inches, and 15 feet, 1 inches. As you can see, between the 25 and 21 foot spans, those are pretty close. So the loading requirements for those were similar enough that we standardized those to one joist type, 16K9.
by 8 inches. And what we needed to design was the thickness of the column. And the load that's being applied is 39 kips. So we ran through some calculations, and we checked the 8 by 8 by 1/8 of an inch, and it actually ended up being 38.9 kips. So it was just under a little bit of strength, and it was also probably a little bit too flimsy. So we bumped it up a little more to the 8 by 8 by 3/16 column, and ran through those calculations again. And the maximum strength of that was 64.4 kips. So the column that we chose was 8 by 8 by 3/16. Moving on to the steel beams calculation. Like I showed earlier, the maximum span was 29 feet. And the hand calculation for this would have been a little tedious, so we modeled this in RISA. And what you're looking at here is this is the beam, and then the point loads right here are the root joists that are pushing down the beam. And this is actually the shear diagram. All the way on the left side, you can see where it's up the highest, and that's where the maximum shear is 17.7 kips. And there's also a moment diagram, and the maximum moment was 24.2 kips. And what you do from there is you go to your design tables and you try to find the beam that best fits. And we needed a W8 section. It fit on the column better than any of the others. And what you do here is the BMP is your maximum moment capacity, which is 149 kip feet, which is greater than the maximum moment applied. And also the shear over here is 89 kips, which is much greater than the shear of 17.7 kips. And for the maximum factor moment, you actually run through some more calculations and find out the strength of this beam at 29 feet is 131.1 kips. So the beam that we chose was a W8 by 40.
As previously discussed, we move into these seismic load categories. And this is one of many tables you can find in your ASC 705 manual and other seismic category places. Our structure will be located here on Fort Hood, near Clean, Texas. It's actually in the lowest hazard zone for seismic events. So it's a really nice place for building something. It's a good location. Glad we chose that one. When you find your basic area, it changes all the factors for your equations. For example, if you were going to build over here, you'd have much, much higher values for your seismic shear. So once we found out we were in a low location area and simplified some of the equations we're allowed to use as per the guidelines in ASC 705. So found your seismic zone, you then have to calculate your T values, which is your response for your 0.2 and 1 second structure responses, respectively. Basically, that's if you're experiencing a seismic event, what does your building do in the first 0.2 seconds, and then what does it do in the first full second of the seismic event? These are modeling values, and they predict what the structure is going to do for the rest of the event. Use those factors and some more equations that we don't get you here, because they're hard to explain and complicated in nature for a presentation of this type. You need to find and seize the best factor, which is a factor that encompasses your entire building's natural period and represents how the structure is going to react to a seismic event. That structure is then multiplied by your weight of the structure. The top half of the wall goes into the shear that's going to be experienced by the roof diaphragm and your lateral force bracing systems, and the bottom half of the wall is transmitted down to the footings. You can come to the design shear for those. So you end up with a final value for ours of 12.38 kips. Not that large of a factor for the size of our building. And again, that's because we're designing a very light steel frame structure here with, as you saw in the columns, very slender members. So if we had a larger member size, we'd have more force.
Moving on to our lateral force bracing system. This is one of the last things we did after we found our seismic load and our wind loads. We actually went through loading scenarios and found our greatest shear. And from the engineer, this is where he selected each of our frames to be. And if the building is shaking side to side in this situation, then frames 2 and 5 would be taking most of the force. And basically, it would be cut in half. This weight above the line would go to 2 and below would go to 5. And like I said, frames 2 and 5 are the controlling factors because they take most of the weight of the structure. And we ran through some basic statics and found out that the force in the members here and here is actually 4.63 kips in tension and compression. And from the engineer, we found that he said to use a HSS 6 section, which is a hollow steel tube, 6 inches. And what we need to do was find the area of steel that we needed. And from the equation here, the BPN is 4.63 because that is the force that's being applied. And Fy is your strength of the steel being used. So from that, you can actually solve for the area of steel that you need. And we came up with 0.123 square inches. And the next highest HSS 6 section was 0.188. So that is the cross bracing that we used in both directions for all threads. We then move on to the moment frame. And the reason the moment frame is there is because if you look on the structure, there's windows where a cross bracing needs to be. So basically you need to do a moment frame rather than a cross bracing. And we modeled this in RISA, and you can see here, these are actually the columns we used, and that is the beam that's being used. And we applied the load of 2.66 kips and checked the reactions. And we found out the maximum shear and the moment in those were very small. They were nowhere near the breaking limit of each of those. And we checked the deflection, and the limit was L over 120. With the 20-foot column, we find out that the deflection limit is actually 2 inches. And from the RISA table here, we find out that the actual amount that is moving is less than 1 inch.
Moving to the calculations for spread foundations. On structures of this size and cost, it's often the case where they don't spend the money or have a geotechnical firm come in and do a soils investigation. And when that happens, you have to go into the International Building Code and the local building codes and find out what they specify the soil bearing pressure to be, just how much the soil can hold. So I went and did that in the National Building Code and the local building code for Killeen, Texas. Found that they specify the minimum value that you can use without soil investigation as 1,500 pounds per square foot. That's a pretty low value, so you're going to have some oversized foundations just based on not doing a direct soil report. I designed 6 foundations based on the loading cases we had for the structure and where they had to go and the size that they had to be for tributary areas of the column. And then I consolidated it down to 3 for easy construction. 6 different spread foundation types on the structure of this size would be pretty confusing for a construction team to have to come into place. So I did some extra calculations and oversized those foundations just to make it more clear and easier for the actually to construct. I'll show you a figure in a moment, but in our particular project, you had to do what's called combined footers. Some of our columns are too close together to have distinct foundations for each one of them. We have 2 that were only 2 feet apart on the columns for the drive-through windows. We have those little jets that come out of the structure, and there's just not enough room for 2 foundations in there. So you have to do some extended calculations to make sure that you proportion your footer, position it right, so you don't get eccentric loading on that, and then have some overturn you have to consider. And then the last note here is that with 1,500 PSI, that number is actually in the building code to resist settlement effects. So they're not so much concerned with the strength of the soil to actually hold it, just to make sure that it doesn't settle differentially. You get some tilt when it settles in one part instead of another part. And just shown here is a typical diagram of a spread foundation. You have reinforced concrete below the soil surface with your concrete rebar on the bottom face. And you have the hooks where you can hold the column in and gravel barriers or anything that's slab on top. Shown here in the legends over here to the side, you have the spread footer diagram layout. These are the actual sizes the foundations are going to be proportional to the structure you see for what we have. And these are actually only just 5x5 foundations. So nothing is crazy oversized. You're not looking at any sort of overlap between the foundations at this point. Moving on, these three foundations pictured here were the ones I had to do combined clear calculations for. You had a large tributary area right here. This is actually 4 feet between those. And you had such a large tributary area coming into this column that necessitated the use of a combined foundation to make sure that they didn't overlap there. Another point on this is that in the entryway, you had some offset columns with beams, and that created a particular loading case where you ended up having more force on the beam and transferring the column than the tributary area actually allotted. So it was another interesting set of calculations that I had to go through. Moving on to the last piece of design, the floor slab. This is what's called a slab on grade. Right? It wasn't actually covered in the concrete design class I took here, so when I went to my meeting with Joe, we talked about the requirements for a slab on grade. It was his recommendation that we went with a 4-inch slab. This required a minimum amount of reinforcement for temperature and turnage. I designed it using a number 3 rebar every 12 inches. My actual recommendation, if I'm doing just a little bit more research, is they end up using a welded wire mesh. And I just don't have the calculations to recommend exactly which one to use. There's a minimum amount of area of steel necessary per foot section of the slab. And so long as the welded wire mesh meets the minimum requirement, it should be sufficient for strength. This diagram here was just sort of a comprehensive look at the way loads flow through the structure. So you get loads applied, gravity loads, inline loads to the roof, wind loads to the sides. Those things are transferred into the columns and then beams effectively and back down into the foundations. On the slab here is illustrated as just a separate element that is non-structural in nature and just supports the weight of the furniture and the people inside of the building. And the last piece we did for the project in our scope was a conceptual cost estimate for the materials involved in a structure of this type and size. Again, this is just to illustrate what the typical cost of constructing a building designed in this manner at about this number of square feet is going to cost somebody. They're calculated using the RS means cost estimator with the time and location factors, actually calculated off of a similar project done here last year from Mother Street. And the total cost of the steel for the building came out just over $67,000. Total cost of the concrete foundations was just over $30,000. The total structure cost is just under $98,000.
Are there any questions at this time?
Nice job. I was looking at the cross bracing, and were they 6 inch square?
Yes.
So 2 of them cross, that's about 12 inches, so that's tricky if you've got an interior wall, and you've got a box around it. So some of these are probably in like a storage room, maybe. But others, it might be a problem being able to box it, but just more. So,
What was the question again?
well, the bracing, like you got shown in the picture too.
Yes.
If that's too thick, you won't be able to put a wall around it. It's in a finished space. Because
Okay,
it's so wide.
so it would be between the walls, is what you're saying. What was the thickness of the walls? It was 8 inches, was it not?
The exterior walls were designed by the architect to be 8 inches. The interior walls we are allowed to have more play with. So most of the frames you see are actually on the interior wall. Actually, that's not technically true. We have one interior frame.
Okay, I see number 3 now, that's like a chase where it could be wider.
Yes, it's
Maybe those are us-
it's a
those are
little
us.
bit wider there to fit the frame.
Okay. All right, thank you.
In your dynamic loading, you talked about what the structure does in the first 0.186 seconds, or the first second. What do you mean by what the structure does?
Well, the way a structure responds to a seismic event is delayed response of sway based on the rigidity of the structure itself. So that's actually why you need the cross bracing to resist the wind and seismic forces. But what I'm saying, what the structure does is how the structure responds in motion to the forces applied to it.
So you're only displacement, not stress or strain?
Correct. We actually checked the displacement because it causes stress and strain in members, and those stresses and strains are much less than the factor capacity of our members, so it wasn't an issue for the actual strength of it. It's just when it moves, it causes additional stresses based on offsets and locations and introduced moments. So that becomes the issue once it starts deflecting.
Yeah, you said usually a soil analysis is not done for this type of situation, but my question is, in fact, has a soil analysis been done?
It is not. As I mentioned, I had to go into the International Building Code and the local structural code for Killeen, Texas, because they weren't willing to spend the money to do a geotechnical investigation of the site. So 1,500 pounds per square foot is actually a pretty standard global minimum for soils, even though I fully expect the soils in this site to be much more robust than that. You have to use the minimum without investigation.
Okay, good job, guys. Got a list of questions. So, let's see. We started off with outlining your dead loads. Some of those were assumptions, mainly the member sizes, I think, primarily. Doing preliminary designs for those members, but then you had to go back, once you determine your seismic coefficients and stuff, since the weight of the building reacts seismically, I don't want to say this. The weight of the building directly determines how the building reacts to seismic forces. So did you go back based on your preliminary designs and kind of revisit those to determine if your initial sizes, if you needed to tweak your initial sizes at all? Or was it kind of an iterative process based on?
We did go back
to
to
sizes?
We did go back after we determined what the full structural loading was going to be on the building and check to make sure all our numbers were sufficient for that load. These are actually the final numbers for what members we chose.
Okay, all right. So in other words, if you assumed initially for gravity loads and stuff, if you assumed a joist that was, 6 pounds per foot, whatever, and it turns out that it ended up being a little bit more than that, you would have had to go back and adjust your seismic forces, basically, I guess, if it ended up being 8 pounds per foot.
Yeah, and we actually overestimated our beam size initially, based off, again, the project that the teachers did last year. They had a much larger span than we did for some of their interior lines of support. So when we assumed their beam would be sufficient for ours, we actually go back in and do some loading, and our beam was lighter than that.
I didn't hear you call out a joist spacing for the bar joist.
That's 5 feet.
5
4
4
inches.
Okay, that was just the maximum. For the columns, let's see, for the gravity loading, the slenderness factor, your K factor, didn't mention that. but-
The KL over R factor, I think it was about 123, and the maximum was 200, so the slenderness factor checked out.
Okay, so for slenderness, it was okay, the overall slenderness ratio, okay overall. The K value you used in that calculation was what?
We used 1.
Okay. So that was with respect to gravity and then for the brace frames as well, because it's a end-to-end connection, right? End to the base, end to the top. Okay. For the moment frames, that's a little different because those are fixed, right? Fixed at the base and fixed at the top. So your K value would be.
I think what we used was 1.2 or 1.4. I'm not exactly sure. We modeled it in RISA and we used the end-to-end connection.
Okay. You'd use fixed. Again, the moment frame would have been.
Yes.
Right. Would have been unstable.
Yes.
I know, I can see it on the diagram. I'll let you know. On the beam designs, back to the beams, unbraced length, you use beam tables through AISC, okay? Those assume that you're meeting a certain unbraced length to get a beam size, okay? What was your unbraced length for the beams?
You want to go to the diagram? Our unbraced length was 29 feet, and yeah, and you can see here the LR factor is 29.9, and
Our maximum unbraced length was the maximum span,
Span.
or largest being of
Right.
29 feet.
Okay, so for beams that are supporting a bar joist, in the future, what you can do is consider the bar joist as brace points. Those will be either bolted or welded to the top beam flange, where you're compression, and that's what you're bracing against. Okay. So you can use the unbraced length of the joist spacing. So your unbraced length for that would become 5.4 feet, and you could then reduce your beam size accordingly. For beams that are parallel to the joist, that aren't supporting the joist directly, okay, those would be supported, those would be braced by the metal deck, which would be directly attached to that beam, and then you could consider the unbraced length in effect to be 0. But so you've gone about it in a conservative fashion, and that's fine. We didn't really get into specifics of unbraced length, so that's fine. In the future, you can use the joist and the deck to brace the top flange of your beams. Okay. The bearing capacity, 1,500, and that was assumed because we do not have a soil boring for this project. Correct. Right? Okay. You mentioned a couple times, I think you said, you used the word oversized a couple times, or conservative, or whatever, I can't exactly remember. I think oversized was where, I wouldn't just throw that out there, because really you don't know. The code is allowing you to assume 1,500, but you really don't know. At Tyndall Air Force Base in Florida, we did not have soil borings, and we assumed 1,500 until they excavated and found peat below the site, which the bearing then became like 200. So you really don't know if it's oversized. I wouldn't, get into that situation where you're talking to somebody, a client perhaps, or your boss, and saying, well, 1,500 was assumed, we oversized these footings. You really don't know if they're oversized until you know. Okay, so kind of watch your verbiage there on that. Alternatively, at the brace frames, where, through the statics, you're going to have the lateral force at the top, you're going to have downward pressure on one side, and you're going to have an upward force on the other. Okay? To resolve that lateral force, was there uplift? Were the footings, so on the brace frame, you could go back and think of it. So on that diagram you've got down below, you've got a lateral force moving the frame, wanting to move the frame to the right. So the column on the right, from static, you're going to have a downward force, a downward reaction, and then the columns on the left-hand side of the diagram, it's going to be going to resist the overturning. Was there a net? Do you know if there was a net overturning or a net uplift at that location based on your dead loads reacting against the overturning force that the lateral was?
It was calculated. The reactions were calculated at the bottoms of each of the columns. I don't exactly remember what they were. I don't have them with me. But I know that they were very small, and we did check for that.
Okay. In some instances with a building that's light, you may not have enough dead load to counteract the lateral loads and the overturning on a given frame, particularly if the frame is narrow and tall. Okay, you can imagine that scenario. So you always want to double check that against, the dead load that you've got, and to see if there actually is a net uplift. Because in that scenario, the gravity loads wouldn't control the design of the footings. Okay, we need the overturning, and we need to check that footing, make sure that the weight of the footing and the soil above it resists the uplift force.
I considered the uplift forces from the wind when I
Right.
designed the footing, and they ended up being 18 inches or 2 feet thick for the bottom footing thickness.
Okay, okay.
Should
So,
be sufficient weight to resist uplift force.
right, is that in essence designing them as a dead man against the frame? Okay. And then lastly, the slab, you mentioned, one of the three, I think number 3 is CRSI and ACI, Concrete Reinforcing Steel Institute and American Concrete Institute. Both of those will give you resources on molded wire mesh, molded wire fabric. And you just basically find it in the table based on the molded wire mesh size, the amount of area you need to meet your minimum for temperature and shrinkage. And that's where you can find that information. Okay? All right. Good job, guys.
All right. Well, let's give them a hand.